So when we talk about calculating derivatives, it's no different than how we've calculated derivatives for almost the last two semesters. We want to take the function and take its derivative with respect to x. And so the only thing that becomes an issue is that in order to calculate the derivative of a function with respect to x, we're really talking about going back to the Cartesian coordinates here. And in order to do that, we need the Cartesian form of the equation. The problem is that these are all conics, and the Cartesian forms of the equations are pretty complicated. For instance, this conic here is parabolic, and to take the derivative of this parabolic equation would require doing implicit differentiation because it would be x in terms of y squared. And that gets to be a lot of work. So when we think about the derivative of a parametric equation, we can rewrite this as looking at the top here and saying, well, this is the differential of the y parametric equation, which is right here. So this is really a dy dt. And this is the differential of the x parametric equation, so this is really a dx dt. And so this ends up being a much quicker way to calculate the derivative if you already have the parametric forms. So that being the case then, and so goes the book definition here. In order to calculate the derivative then, the Cartesian derivative, we can take a ratio of the parametric derivatives. And of course, we want a derivative that's defined, so we have this criteria, then the denominator can't be 0. Because that wouldn't be a defined value. So that being the case, the Cartesian derivative with respect to time of the x parametric equation would look like 2t plus 3, and the y derivative with respect to time would look like 2. And so then the Cartesian derivative dy dx then is going to be the y parametric over the x parametric. So there's the definition of the Cartesian derivative with respect to the parametric variable. And so if I wanted to calculate the derivative at a given point, for instance, let's calculate it at t equals 0. So when t equals 0, the Cartesian derivative dy dx equals 2 over 3. And so if that's the case, that's the value of the derivative, then that is also the slope of the tangent line. And so when t equals 0, x equals 0 and y equals 0. So we're looking at this point, and at that point we have a slope of the tangent line of 2/3, so up 2 over 3. So our slope of the tangent line looks something like this. And so if we take a look at that and find the equation of that line, then we have an intercept of 0, we have a slope of 2 over 3. So the equation for this line looks like y equals 2/3 x plus 0, or just 2/3 x. If we want to take a look at where's the derivative undefined, then we can just take a look at this expression, 2 over 2t plus 3. Where is that undefined? Well, it's going to be undefined when the denominator equals 0. So we're really looking at, if this is the Cartesian derivative, we're looking at it's undefined when 2t plus 3 equals 0, which is a t of, let's see, bring the 3 over as a negative, divide by 2, a t of -3/2. And so really what we're saying here by setting this equal to 0 is we're saying the derivative of the x Cartesian coordinate, in other words, the denominator of this expression here, has to be set equal to 0. So we're looking for this condition of when it's undefined. And so when t is -3/2, where is that? Well, that's a x value of 9/4 plus 9/4 plus a -9/2. So that would be a -9/4. And that would be a y value of 2 times 3/2. So that would be a -6/2, or which would be a -3. And so if we look at that -9/4, that's 2.5, basically. So -1, 2.5, down 3, 1, 2, 3. We're talking about right here. Excuse me, 2.25, -2.25. I said that wrong. So that's -2.25. So -1, 2.25, and then down 1, 2, 3. So here is where the derivative is undefined. And if you think about the derivative, the slope of the tangent line, right? That tangent line here is vertical. So when we're talking about the derivative being undefined, we're talking about finding those points of vertical tangency. And we'll talk more about that as we get into other examples. As we look at this one, it says find all points of horizontal and vertical tangency to the curve. So we're starting to get into that phenomenon of horizontal and vertical tangency. Here's a picture of the curve. We know it's parabolic because we have a t² and a t. And if we would solve this for t and plug it in, it would be looking like t equals x minus 1, and y equals then x minus 1 quantity squared plus 3t. So there's our parabolic equation. It is a function, y equals x squared. So this is 3x minus 1, excuse me, I should finish that out. And so we're looking at x squared minus 2x plus 1 plus 3x minus 3. So we're looking at a parabola that looks like x squared plus x minus 2. Which makes sense because if we factor this, we get x plus 2, which would have a solution at -2, and x minus 1, which would have a solution at +1, or a 0 at +1. So that makes sense. So this is the parabola, and when we look at this, we're talking about horizontal and vertical tangencies here. So horizontal tangency is going to be a horizontal line. So visually, we can see there's a horizontal tangency right there at that location. As far as vertical tangencies go, there are none. There is nowhere in this parabola where we can draw a vertical tangent line. So when we take a look at the Cartesian derivative, and that's what we kind of casually call the derivative, and we look at it in parametric form, it looks like this. And so when we're talking about a horizontal tangent line, we're talking about a slope of 0. That's the value of the slope of a horizontal line. And so in order to get a slope of 0, we would need to have a value of 0 in the numerator. And so really what we're setting ourselves up for here is a derivative. We need to take the derivative of the y parametric equation and set it equal to 0. So here's our y parametric equation. The derivative there is 2t plus 3. When we set that equal to 0 and solve for t, move 3 to the other side, divide by 2, we get a t value of -3/2. So there's our value for t. And if that's our value for t, if we want to find the point of horizontal tangency, we know there are no vertical tangencies. When it says find all points, it really implies giving the points in the form that is graphed, and that's on the Cartesian plane. or the xy plane. So we really have to figure out the xy coordinates. So the value of x at a negative 3/2 would be plugging that in there, negative 3 over 2 plus 1. So the plus 1, this is 2 over 2, so we're talking about negative 1/2. And the y value is negative 3 over 2 quantity squared plus 3t. So that's a little more math involved there. So we're talking about 9 over 4, and I should plug that in here, minus 3 over 2, plus a negative 9 over 2. And of course the negative 9 over 2 is really a negative 18 over 4. So we're looking at negative 9 over 4 for our y. So we're talking about a horizontal tangency at minus 1/2, comma, minus 9 over 4, which would be 2 1/4. And so when we look at that minus 1/2, minus 1/2 down 1, 2 1/4, that gets us that vertex of our parabola. So hopefully not a big surprise. All we really did is find the vertex of that parabola for the point of horizontal tangency. Okay, so for this example, and I'm just going to talk about horizontal and vertical tangencies again. By inspection, you could almost answer that question. The horizontal tangencies are here and here. So if we would just kind of sketch those in, here's a horizontal tangency on this ellipse, and here's a horizontal tangency on this ellipse. So we're talking about 1, 2, 3. So this is a y equals 3 equation. Or in other words, we have that point here at 0, 3. And we have that point here at 0, minus 3, or an equation of y equals minus 3. And then those vertical tangencies, or what we would call those points of undefined slope, is right here and right here. That's where we have our vertical slope. So we're talking about the point 0, 2, excuse me, not 0, 2, 0, 1, and 0, and I really messed that up. Not 0, 1, but 1, 0, and minus 1, 0. So we're looking at these, if we had to write an equation for the vertical tangency, it would be x equals 1 and x equals minus 1. So with the ellipses, a lot of times you can just do those by inspection. So we want to really evaluate the derivative here at this given point of theta of 0. So looking at a theta equal to 0, if we plug in a theta equal to 0, let's just go ahead and plug in and find those values. X equals the cosine of theta, so the cosine of 0 is 1, y equals 3 sine theta, and so 3 sine of 0 is 0, times 3 is 0. So we're looking at the point 1, 0, which we've already identified here. So by inspection, we can see that we have an undefined derivative here. From a algebraic standpoint, if we take a look at the Cartesian derivative here and write it in parametric form, when we're talking about evaluate the derivative at theta equals 0, well, the derivative dy dt, so dy dt is going to be 3 cosine theta, and dx dt is going to be minus sine theta. So when we plug in the value of 0 here, we're going to get 3 cosine 0 radians or degrees, that doesn't matter because 0 is 0, over minus sine of 0. And so looking at this, we've got 3 over 0. And so that is also an indicator there that we have an undefined slope.